Hello and welcome to this RAIS online webinar. I'm Lodovico Giaretta, and today I will talk about machine learning and data privacy, how these two terms are related to each other, and whether we can have both of them, or if there is some kind of issue combining these two topics. So to understand why this is something important to consider, I will start by highlighting how machine learning is really becoming important for our society. It's changing in many ways the way we live. And of course, we can all see this in our online experiences. So for example, which items we get recommended or which news we get to read on a news website, which videos are suggested to us by our favorite video platform. But it also affects and shapes our experiences in the physical real world. So how our basic services work, for example, our transportation, our healthcare, our scientific research, they all employ machine learning. And machine learning is, for example, helping doctors make correct decisions more quickly for their patients. It's helping medical research, understanding how proteins behave, for example, and how certain medicines can interact with certain medical conditions. So it is really an important core aspect of the way we live, and it's an important tool for us to shape our future. So let's go a bit deeper and see, but then what is machine learning? What is a machine learning model? Well, a machine learning model is, first of all, just a piece of software. But while for most software, the developers that build the software have to specify how the software is going to perform a certain task. On the other hand, with machine learning, we don't have that, because there are many tasks for which it's not that easy to explain, to write down in a piece of software how the task should be completed. So for example, we all are able to distinguish the picture of a dog from the picture of a cat, but it is very challenging to tell a computer to do it, to tell a computer how to understand if something is a cat or a dog. And this is where machine learning comes in. So machine learning is a kind of software that can learn how to complete a certain task. So it can, for example, learn how to recognize a cat or a dog without being explicitly told what are the differences. However, machine learning models can only do this because they have many examples that they can use to learn. We provide them with a lot of inputs. So in the case of distinguishing cats and dogs, we have to provide many pictures of cats and many pictures of dogs to our model, so that our model can learn how to distinguish them. Our model can be trained on this task. And so many examples, many input examples means a lot of data that must be fed to these models. And this is where these privacy concerns with machine learning come in. This is where we actually want to ask ourselves, can we put together machine learning and data privacy? And we can see that in a typical pipeline for training a machine learning model, what will happen is that a company or an organization that wants to train a model will first of all collect a lot of data that is needed for the training. And this data will typically be collected from the users of whatever service the company is providing. Then the company will use this data to train the model, so the model can learn how to complete whatever task it needs to complete. And then the organization will use the model to improve their services, or maybe sell the model to other companies who might be interested in using it. And so here come the issues. The data that has been collected for training the model might be private, sensitive data about individual users. And because this data has been collected by the organization, then members of the organization can actually see the data in their database, in their warehouse. And therefore, they have access to sensitive data that maybe they shouldn't have access to, because this undermines the privacy of the users. But this is just the most obvious issue. There is another one that is harder to notice. Machine learning models don't really behave like humans, although we use terms such as learning, so terms that we typically use for humans to refer to machine learning models. Machine learning models behave differently. So a person will hardly remember what were the first pictures of dogs and cats that that person has seen. And so the pictures that that person learned to distinguish cats and dogs on. But on the other hand, the research has shown that machine learning models can actually retain quite a lot of memory of the data they were trained on. So that actually it is possible, by looking at a trained model, it is possible to reconstruct a lot about the data that it was trained on. And this is another way that the privacy of the users is undermined. And so these are the issues that we need to solve if we want to use machine learning in our society, but at the same time guarantee the privacy of each individual. And so let's go step by step. The first part, the most obvious one, is to hide the data from the organization that needs to train the machine learning model. How can we do that? Well, the first and maybe most obvious idea is that we can obfuscate the data. So if we look, for example, at some of my personal information, my age, weight, height, and the town I live in, this is some very specific information. There are not many people in the dataset, potentially, that have the same age, weight, height, and location as me. And so it is very easy for people looking into the data to spot me and to distinguish me from other people, to tell whether I provided my data or not, or to cross-check the data that I put here with the data that I put in another company, and build a profile of me and track me across different services. So if we want to prevent this, one thing we can do is that we can make the data less specific. We can anonymize the data. And we could do this, for example, by, instead of providing age 26 years, we can provide a range. So my age is between 20 and 30 years. And the same with the other information. And for my location, for example, we can move to a lower granularity. So we can say, instead of the specific town, which county I'm living in. And so in this way, now the anonymized columns contain information that is less specific. There are now many people that have those characteristics, many people in Stockholm country that have that age range, that weight range, that height range. And so it is harder to distinguish me, to pinpoint which data point belongs to me, which one is my information, or even if I am in the data set or not, if I provided or not information. But there is also another possible approach, which is instead to provide some noisy data. So instead of saying I'm 26 years, I will randomly choose to add or subtract a few years. So in this case, I chose to add 1 year. So I will report I'm 27 years old, and I will report 67 instead of 69 kilos. And maybe I will report a city that is slightly north of the one where I live. And in this way, now this data point is harder to connect to me, because that 27 years old, it might be 26 plus 1, but it can also be 29 minus 2. So someone else who was 29 years old might have decided randomly to reduce their age by 2 to add noise. And so all these techniques, they focus on making it harder to spot who provided data and to connect the data to people. And if we go more into the literature, we can see, for example, that in the domain of anonymization, the most common approach is called k-anonymity, in which we want to guarantee that for every bucket, for every possible set of ranges, so for example, the bucket in my case will be from 20 to 30 years and from 60 to 70 kilos, and that height range and Stockholm County, we want in each bucket to have at least k individual users, so that if someone looks there, someone will always find at least k different data points, and will not be able to connect each of them with one specific user. If you want instead to go for the second approach of adding some noise to the data, then we have what we call local differential privacy, where we just add noise and we compute how much noise we should add in order to achieve a certain level of privacy and make it hard to a certain threshold of hardness to recognize individual users. However, these approaches present some limitations. And the main one is the fact that when we apply them to machine learning, they actually have strong negative effects on the results. These approaches are pretty good when the organization that accesses the data wants to compute some statistics on the data, like what is the average age, or what do young people prefer compared to older people. But machine learning models have the capability to connect very specific information and to extract insight from very specific combinations of different input information. And by adding this noise to the input data, or by removing the precision by using ranges instead of specific values, we are actually removing much of the input information that makes machine learning models better than alternative approaches. And so that is the limitation of data obfuscation techniques. So we might want to ask ourselves, is there a way that we can protect the data without having to ruin the data, without having to remove information from the data? And one idea could be to encrypt the data. So each user will encrypt their data when sending it to the organization, and the organization will store encrypted data, and the organization will not be able to see the data because the organization, in this case, we assume the organization does not have the keys to decrypt the data. The organization is not able in any way to look at it. But then if the organization can't see the data, how can the model see the data and be trained on the data? And for this, there are at least two approaches. The first one is called trusted execution environments. And this consists in having specific computing hardware, so specific computer chips that are able to decrypt the data and use the data without leaking it to anything external, and in particular, without leaking it even to the owner of this chip. So even the organization that bought this chip and installed this chip on one of their computers, even that organization would not be able to see the unencrypted data the unencrypted data stays inside the trusted environment, and there is no way to extract it. And also this environment will provide an attestation, a proof that a certain piece of code has been run inside it that trained the model without leaking the data. Another potential solution is to use something called homomorphic encryption. This consists in encrypting the data using certain techniques that allow computations to be performed on the data without decrypting it. So the computation that is necessary to train the machine learning model can be performed on the data without needing to first decrypt it. However, both these approaches present some limitations. One limitation is the complexity of this kind of setups and potential issues such as security vulnerabilities in trusted environments that can actually remove these guarantees of not being able to exfiltrate the data. But most of all, the main issue is that of efficiency. Both trusted environments and homomorphic encryption incur a very high overhead compared to normal unencrypted operations. And therefore it becomes much slower and much more expensive to train large machine learning models with these approaches. However, there is a lot of research going on in this area. And so we can expect in the next few years higher efficiency and more security in the use of these approaches. But there is a third family of solutions that we can use, and that's that of massively distributed training. So this comes from the idea that our problem is that we share the data with the organization to train the model. But what if we removed this data sharing step altogether? What if instead each user kept its own local data private, didn't share it with anyone, and instead performed the training on the model locally on its own device, so on the smartphone or computer that generated the data, rather than sending the data out to a server? So instead of bringing the data to the model, the idea is to bring the model to the data. The problem with this, of course, is that each individual user does not have enough data. As we said, a machine learning model requires a lot of data to learn. So the users need to collaborate with each other in order to build a model that is actually good at its task. One way to do this is to use what we call federated learning. So in federated learning, every user, as I said, has its own local data that will never be shared, and each user can train a model on that data. And that model will not be a very good model because it has been trained on too little data. It is not very good at its task. But then what can be done is that the users can share their models, not their data, just their trained models, with the organization. And so each user will be sharing a different version of the model because it was trained on different data. And then the organization can take all these local models that are not very good and can combine them to produce a better model that takes some knowledge from each of the local models and is therefore better than any individual model at solving the specific task. And then the organization can take this new global model that was produced and it can send it back to the individual users. And then this cycle is repeated. Each user will take the global model and will train it more, give it another round of training, give it again, letting it look at the data and improve. And in this way, the global model will then again become a number of different local models, which will then be reaggregated by the central organization until, after several iterations, the model has become good enough at its task. And at that point, that final global model is ready to be used. However, federated learning also has its own issues that are actually introduced by moving to this distributed architecture. And the first issue is that the organization is now collecting and seeing a lot of local models. And if you remember, we discussed that from a model, there is the risk that by looking at a model, someone will be able to reconstruct some of the data that the model was trained on. And if that is true for a fully trained model that has been trained on a lot of data from many users, then it's even more true when the models being used are actually only partially trained on little data from a single user. Each of the individual models that is sent to the central organization could potentially reveal a lot of information about the data of the individual users. And so it is necessary to trust the central organization to not try to extract this information and to not behave badly by trying to extract information from these models. The second issue is actually the opposite, where instead who is bad is not the organization, but rather one or more of the users. So malicious users can actually send bad models, models that behave very poorly at the task to the central organization. And they might want to do this to ruin the model training for everyone, so that once the models are aggregated, the global model that is obtained is actually not that good or even very bad at its task because of this influence from these bad models sent by malicious users. So this is also an area that has seen a lot of research in recent years. So a lot of work has been going into how to solve these issues. Researchers have already come up with some solutions and are now improving upon them. So this is also an area to take into consideration a lot. It will change a lot in the next years and become potentially much more advanced. But there is also an alternative to federated learning that sidesteps some of these issues, although it has received way less attention. And that is the area of gossip learning. So in gossip learning, what we do is that we completely remove our central organization and we only have the users to work with. And what the users do is that they share with each other their models in a peer-to-peer way, and they combine these models that they receive from each other to produce better and better models in a way that is not that different from what we discussed for federated learning. So, for example, the first user down here might share a model, let's call it model A, with this other user, who might then combine this model A with its own local data and its own locally trained model and produce a new model, let's call it model B, and maybe share it with another user. And then this other user might do the same thing and merge this model C that it has received with its own local data and its own local model and do some more training and produce model B and then send it to another user. But then this other user might also have received a copy of model A in the meantime from our first user. And so now it has received multiple models and it can merge them and do again merging A and B with the local model, train on the local data, and produce yet another model, let's call model D, which will then be sent to someone at random. And by going on like this, exchanging models one with another over multiple iterations, what happens is that the models at each user will actually become better and better and gain more and more knowledge, like the global models in federated learning, until they are ready to be used. However, the issues of gossip learning are one, that there is no official global model, so there is no way to pick one of the model of the users and say that is our final model. Instead, every user will have its own final model, which might be even so slightly different from the others. And the major limitation of gossip learning is that it has not been really studied a lot, and so there are still a lot of open questions about how to optimize it, how to make it secure. But this is also a promising area that has received quite some research. And this closes the first and longest part of this webinar, which was about hiding the data. And so if we now assume that we managed to achieve this goal with one of the techniques we discussed, if we manage to hide the data and train a model without disclosing the data, then now we are faced with another issue, which is the one I mentioned before, that the organization that produced the model or any other organization that gets to see the model will be able to extract data from it, will be able to extract a lot of useful information about which data points, which users were used in the training, and potentially extract some of these input data. And here, one solution is actually something that we've already seen, and that is differential privacy. So before we were talking about local differential privacy, in which we add some noise to our data before sending it to the organization, so that it's harder to connect the data to the individual users. But differential privacy is more general, and it can actually also be used to apply noise to the output of a computation. So for example, to a trained model, which is the output of a computation in which the model was trained. And so by adding noise to the final trained models, or by adding noise during the training process of the model, we can actually make it so that the model still is able to solve the given task with a very good performance, but at the same time, it is not that easy to reconstruct the original training data from the model itself. So we achieve a good model without giving up on our privacy. And so now to conclude, what are the ways to protect our data when we are training a machine learning model? And in the end, is it really possible to have both, to have the best of both worlds? Advanced machine learning that can improve our society, and also data privacy to protect the sensitive data of each individual person. And the answer is that yes, we can have the best of both if we apply one or more of the techniques that we discussed. So when it comes to protect our data during the training process, we have data obfuscation techniques like key anonymity and local differential privacy, that make the data harder to connect to the individual users. We also have the possibility of training on encrypted data using either trusted execution environments or homomorphic encryption, so that the data can be preserved in its original form, but without making it visible to the training organization. Or finally, we can actually avoid sharing the data altogether and use either federated learning or gossip learning to train the models on the user devices where the data is stored, and then share them to build better and more powerful models. But then we also have to remember that we need to protect our data even after model training to prevent people from reconstructing the data by looking at the model. And here, even if we didn't mention it, data obfuscation is again an option, because if the original data during the training phase was obfuscated, then it will also the data that can be reconstructed by looking at the model will be obfuscated, and so we don't run any risks. But as we discussed, this has the issue of reducing the quality of the model, and so it is maybe better to use model obfuscation techniques, such as differential privacy, adding noise to the model itself, to make it harder to, let's say, reverse engineer. And so, with this final summary, I would like to thank all of you for listening to this webinar, and I hope that this gave you some insights into machine learning and data privacy, and I hope this will maybe help some of you decide to do some research or some work in this area to further improve this topic. So thank you again, everyone.